I welcome all the participants of ICMD 2022 and express my gratitude to Professor Bhaskar Bhattacharya and Professor Neelam Srivastava for giving me an opportunity to present my research work. The title of my work is Design of Two Novel Dyes Having Maximum Absorption in the Infrared Region, a DFT Investigation. So as the title suggests, the work is theoretical in nature and it investigates the properties of organic dyes which have the absorption profile in the infrared region. These dyes can be utilized in the dye-sensitized solar cells or DSSCs. The DSSCs can also be prepared on flexible substrates as shown in this figure. The original concept and idea of DSSC was given by Professor Michael Gratzel and Brian O'Regan in 1991. Since then, researchers have tried to improve the efficiency of DSSCs as can be seen in this figure. The overall efficiency of DSSCs have increased a lot in the previous times as compared to other non-silicon based solar cell technologies. This slide shows the working mechanism of DSSC. In the first figure, we can see the different layers of DSSC. The first layer is the FTO, followed by the TiO2. The dye is adsorbed on the TiO2, followed by the electrolyte and the counter electrode. When the sunlight falls on the dye, then the electrons are produced by the DSSC. These electrons then travel through the load. In the second part of this figure, we can see the different steps of the electron formation in the DSSC. Now I will talk about the necessity of the designed novel dyes. Now, as most of the solar energy is concentrated in the visible and infrared region, it is necessary that the dyes must absorb light not only in the visible region but also in the infrared region. The energy levels of the dye should be in alignment with the energy levels of the metal oxide and the electrolyte. This ensures that the electron and hole transfer takes place efficiently. Now, in order to transfer the electrons to the conduction band of the semiconducting material, the LUMO of the dye must be higher than the conduction band of the metal oxide, and the HOMO of the dye must be lower than the HOMO of the electrolyte. Now the question arises, why we require IR active dye sensitizers? Near infrared dyes are available in a wide spectral range from 700 nanometers to 2000 nanometers. These near infrared dyes can be used either singly or in combinations to create custom spectral filters for multiple applications. These applications include laser safety eye wear, security, welding protective eye wear, heat shields, telecommunications, digital printing, light filters, and much. In the current work, we have designed two novel dyes based on the DPi-A and DPi-AA model for application in DSSC. These dyes have the absorption profile in the infrared region. The first dye is carbazole thiophene naphthalimide and the second dye is carbazole thiophene naphthalimide benzothiazole. These dyes have the same donor, which is carbazole, and the same pi bridge, which is thiophene. The optimized structures of the two dyes are shown in the current slide. Both the dyes were optimized by using the density functional theory. The functional B3LYP along with the basis set CCPVDZ was utilized. All the calculations were performed by using the Gaussian 16W software package. The frontier orbitals, that is HOMO and LUMO, for the two dyes are shown in the current slide. By observing the HOMO and LUMO, we can analyze the changes in the electron distribution. Charge density difference is shown in the current slide for the two dyes. Charge density difference is associated with the difference in the charges between the excited state and the ground state. The blue part of the figure represents the positive change, whereas the red part represents the negative change in the charge difference. Table 1 shows the energies of HOMO and LUMO and also the energy of the HOMO-LUMO gap. In the table 2, the maximum absorption wavelengths along with the oscillator strengths and the light harvesting efficiency for the two dyes have been shown. In this table, the values of free energy change for electron injection and the reduction potential are shown. In the table 4, the values of dye regeneration energy and the open circuit voltage for all the dyes are shown. In the table 5, the oscillator strength and the associated molecular orbital contribution for the maximum absorption wavelength are shown. Now I will summarize the results of my research work. Now, in order to design good IR absorber dyes, the double acceptor moieties in the DPA model are useful. From the results of HOMO and LUMO charge distribution, it is clear that the HOMO lies mainly over the donor and the pi bridge of the dye sensitizers. The LUMO is spread mainly over the acceptor moieties in both the dye sensitizers. From the CDD plots, we can visualize that the charge is mostly spread over the whole molecule, whereas its shift is slightly towards the acceptor side, which is shown by the blue color. The present results confirm that the model based on DPA and DPAA design are suitable for absorption in the infrared region. We also found that the dye 1 has the maximum absorption wavelength at 1432 nanometers, whereas the dye 2 has the value at 1351 nanometers. The light harvesting efficiency for both the systems are found to be similar. Charge injection energy is negative, which shows that the charge will be transferred at a fast rate to the semiconducting site of SnO2. Dye regeneration energy for dye 1 is higher, which is because of the lower LUMO level as compared to dye 2. The open circuit voltage for dye 2 is higher as compared to the dye 1. This shows that the double acceptor strategy is better for designing the efficient sensitizer. With this, I conclude my presentation. Thank you everyone for your patience.